All right, today we're going to write Lewis structures for molecules and ions containing covalent bonds using the periodic table. We're also going to write resonance forms for molecules or polyatomic ions that are not adequately described by a single Lewis structure. We're also going to talk about something called formal charge and some exceptions to the octet rule. The quest for this play posit is Lewis structures. So, drawing Lewis structures is something that we did in honors. It is mostly review, but we're going to add some little clarifiers to a lot of the things we did in honors. The main steps are the same. You want to calculate your total number of valence electrons for your molecule. Then we're going to draw our skeletal structure. So a skeletal structure, you pick a center atom. The center atom is going to be the one that is least electronegative. And then we're going to connect our bonded atoms using a dash to our center atom. The dash represents 2 electrons. We're going to place the remaining electrons around the outer atoms first to give them a complete octet, and then we'll worry about satisfying our central atom. If we have any electrons left over, you put them on the central atom. If not, you will have to move some of those lone pairs from your outer atoms in to form multiple bonds, so things like double or triple bonds. If you use the saying, some people can't stand distracting children, it's a good way to sum up this process. So sum, place, connect, subtract, distribute, and then convert. So let's fine-tune some things. Hydrogen atoms only form single bonds. If we think about the electron configuration for hydrogen, it's only in the 1s orbital. S can have a max of 2 electrons. Therefore, it can only form a single bond to give it a 1s2 configuration. Can't do anything more than that because there are no other orbitals for those electrons to go. Oxygen usually does not bond to itself with the exception of elemental oxygen, which is diatomic, ozone, which is O3, superoxides and peroxides, and all of those things we do not see very much. Polyatomic molecules and ions often consist of a central atom. Again, it's the least electronegative one, and it is surrounded by terminal atoms, usually oxygen. But it can be things other than oxygen too. Depends on the polyatomic. Lewis structures tend to look symmetric. That is true. If the structure is an anion, you want to add electrons for the negative charge. If it's a cation, you want to subtract for the positive charge. So let's look at ammonium, NH4+. We know there are 5 valence electrons for nitrogen. There are 4 for hydrogen because it's 1 per hydrogen. And then we have a positive charge, so we need to subtract out 1 because we have 1 less electron than normal. This would give us a total of 8 electrons. I can tell you when it comes to counting up the total valence electrons, more often than not, it will be an even number. There are a couple exceptions that have odd numbers, but we're not really going to see them very often. So if you get an odd number, make sure you accounted for your negative or positive charge. Check that your structure is the best possible arrangement of atoms using the formal charge check. We'll talk about that at the end of this lesson. More than one identical structure may have resonance. That's true. We'll talk about what resonance is shortly. Exceptions. We're going to look at expanded valence today. If you have an expanded valence, that means you probably have a d orbital that can accept more electrons. It also happens when we have more electronegative elements bonded to our central atom that pull electrons away from the central atom, thus leaving it a little deficient. You'll see this a lot with phosphorus and sulfur because they are in period 3 and they can have the ability to put electrons in a d orbital. We have radicals, which are odd numbers of electrons, and then an incomplete octet. Hydrogen's good with 2, beryllium's good with 4, and boron is good with 6 electrons. All right, so let's do some practice drawing. One other thing that's good to know is CNOPs. Kind of looks like Cyclops, or sounds like Cyclops. CNOPs, those are the 5 elements that typically form double bonds. There are a couple exceptions when we look at some of the noble gases. but we're not really going to see that too much. If you have C, N, O, P, or S, those things do have the ability to form double bonds to become more stable. All right, so we're going to look at the first one, nitrogen gas. Nitrogen gas, that is diatomic, that is N2. First, let's find our total. We know that there are 5 valence electrons times 2 atoms. We've got a total of 10 electrons. We're going to place them and connect them. All right. So I've used 2 of my electrons total, so I need to subtract out. And then I need to distribute. I can place electrons around my atoms, but I only have 8 to place. My goal is to make everybody have 8. So let's start on one side. 1, 2, 3, 4, 5, 6, 7, 8. All right, I've used all 10 electrons. I have a problem though. The one on the left has a satisfied octet, the one on the right does not. So this is where the convert comes in. I need to take a pair and move it to form a bond. All right, so that makes things a little better. If I cover this one up, well, it was working earlier. If I cover this one up and look at the one on the left, it still has its 8, which is good. But then when I cover that one up and look at the one on the right, it only has 6. So I still don't have quite enough. I need to take another pair and convert it to another bond. All right. And I end up getting a triple bond between my 2 nitrogens. All right. In this way, each nitrogen is sharing 6 electrons, and it each has a lone pair for a total of 8. Okay. Carbon dioxide gas, CO2. All right. Total, we've got 4 valence for carbon, and then we've got 6 valence per oxygen times 2. That's going to give us a total of 16 electrons. Now, to figure out which one goes in the center, again, we have to look at which one is least electronegative. Oxygen is 3.5, that is the most, in comparison to carbon, which is only 2.5. So carbon is going in the center here. So let's place carbon's in the center. Let's connect it to each of the oxygens. I like to draw dots at the end of my lines. You don't have to draw the dots at the end of your lines, but it helps me to count. I've used 4 electrons, so I've got 12 left. So let's place them. I want to make each of my oxygens happy first. We work on the outside and then go in. All right. Those are my 12. Oxygens are both satisfied by the octet rule, and carbon is not. So we need to convert. Let's take a pair, make it a double bond, and still not good. So I need to take another pair from the oxygen on the opposite side. All right, there you go. I got 2 double bonds. I've got 8 electrons being shared with carbon and no lone pairs. For each oxygen, there are 2 lone pairs and 2 bonds. All right, let's look at water. Water we know is H2O. All right, so 2 times 1 valence electron for each oxygen, or for each hydrogen, plus 6 for oxygen, gives me 8. 8 electrons. Now, if we're thinking about our, why is it doing that to me? If we think about our electronegativity, hydrogen is the least electronegative, but why can't it be in the center? It can only form 1 bond. It is a terminal atom. So yes, oxygen is actually going to be in the center here. We're going to connect each of my hydrogens to it. I've used 4 electrons in total from my 2 dashed lines, therefore I have 4 remaining. Boom. Water's easy. You could also draw water like this. This would also be a valid structure. That one's actually more geometrically sound if we're looking at the shape, which we'll talk about in a later play posit. But if you draw this, this is acceptable as well. So resonance. We can often draw more than one valid Lewis structure for a molecular ion, and this specifically comes into play when we have double and triple bonds. No one Lewis structure can adequately describe the actual structure of the molecule because of the double bond that is there. That double bond can essentially be moved around the atom into a bunch of different positions. So as a result, the actual molecule will have some characteristics of all the valid Lewis structures we can draw. The reason for this is because the electrons in that double bond essentially become delocalized. And we're going to look at that a lot in terms of ozone. We're going to also look at it in terms of a molecule called benzene. So benzene looks like this, and benzene has hydrogens sticking off of it, and at each of those centers is actually a carbon. So this is benzene. You'll see that these double bonds kind of create a network. The other way I could draw benzene is like this. The double bonds have just shifted. What happens is, and we'll look at this more when we get into the 3D shapes, because these electrons can move positions in the double bonds, they're considered to be delocalized. So in reality, what's happening is we have this network of electrons that flow almost in a circular fashion between the adjacent carbons in the benzene molecule. So in a sense, it makes it more stable because those bonds can move around. And since they can move around, those electrons in that double bond system are kind of equally shared. So when we look at something like ozone, that's very important because while we can draw ozone with a double bond and a single bond, if we were to look at the bond length in reality, we see the bond length is somewhere in between that of a single and a double bond. It's because those electrons are delocalized and they're almost shared equally across the whole molecule, as you see here. Hence why we have a system of dashes. If we were looking at benzene, it's more like we have a system of dashes all the way around, and because of that, you sometimes see benzene drawn like this with a giant circle in the middle. That just means that the double bonds are the electrons in the double bonds are equally shared across the whole molecule. So what happens is when we have resonance, it stabilizes our molecule. Maximum stabilization comes when the resonance forms contribute equally to our hybrid. We know if we were to look at these two versions here, the double bond would be shorter than that of the single bond, but in reality, those electrons are being transferred across the entire molecule, and therefore we get a hybrid. And with that hybrid, the bond length is actually somewhere in between. When we draw resonance structures, we have to draw all possible structures to account for what's truly happening. So this is what's truly happening here, but when we draw them, we have to draw all the possible forms. We draw the possible forms by drawing brackets around the molecule and then a double-sided arrow. Okay. You'll see there's also these positive and negative charges here. That comes into formal charge. We'll look at that shortly. So let's do a couple. Let's look at carbonate. So carbonate. All right, CO3 with a 2- charge. All right, remember with your total, you've got 4 for carbon, you've got 6 for oxygen. What do you do with that negative charge? Negative charge means you've got additional electrons, so you've got to add. So in total, we've got 24 electrons for carbonate. Carbon goes in the center. I've got my oxygen, and another oxygen. And I've used 6 of my electrons. I've got 18 remaining. So I should go ahead and place my pairs. And I'm out of electrons. What do we see? Well, we see that carbon is deficient. I need to make a double bond. Okay. And when I'm drawing a polyatomic ion, I need to draw brackets of the charge on the outside. This is a valid structure for carbonate. My question is, why didn't I put the double bond on the right side, or even on the bottom? Well, I certainly can do that. Doesn't matter which, as long as you draw all the possible forms. I could have easily drawn this structure like this, Or I could have also drawn it like this, the double bond down below. It is still the same molecule, still the same charge. All are acceptable. Okay. Let's look at nitrite. So nitrite, NO2 with a 1- charge, NO2 with a 1- charge. So we've got 5 valence electrons for nitrogen, plus 6 times 2 is 12, plus 1 for my charge. I've got a total of 18 electrons here. All right, nitrogen's in the center. I've got 2 of my oxygens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, and then I've got 13, 14, 15, 16, 17, 18. Okay. I see that it's not deficient, so I'm going to take and make a double bond there, and I've got my negative charge. Perfect. Can I make that double bond on the other side? Certainly. And do the same thing. Resonance stabilizes this sucker. All right. Boom. Cool. So when we're looking at the octet rule and some of our exceptions, this is going to be our area of focus here, energy level 3. When we're in energy level 3, we are benefited by the fact that there is this D sublevel when we get to energy level 3, and that will help explain some of our exceptions. So when we have an odd number of electrons, we form what's called a radical. These you'll see a lot more when you get to organic chemistry. You won't really see them as much for now. But 2 examples are NO and NO2. The ions or molecules with less than an octet, we see beryllium hydride and BF3. Beryllium likes to form 2 bonds and have 4 electrons total. Boron likes to have 3 bonds. Okay. Now, the last 3. When you have an expanded octet, more than 8 valence electrons, you typically see this when you have phosphorus or sulfur because they're not very electronegative. When they're bonded to things that are electronegative, all those electrons are being pulled away from phosphorus and sulfur, and it creates this deficiency in electron density for phosphorus and sulfur. And as a result, it allows phosphorus and sulfur to form additional bonds to make sure it has a satisfied orbital. Since there's d orbitals there in energy level 3, they are able to do this because they can form additional space for electrons. So with phosphorus, so PF5, we can form something like this. Remember, when we're looking at an atom in 3D space, we've got the X, Y, and Z plane. So this one can actually add extra electrons on that plane there. Extra atoms and electrons, I'm sorry. So P has 5 valence plus 7 times 5 for fluorine. This gives it 40 electrons total. We've used 10 of them from the 5 bonds, which means we've got 30 remaining. All right, oops. And then they just go around all of your fluorines and they become satisfied. Okay, so that is perfectly normal. You'll see phosphorus breaks the octet rule. It has more than 5. We're going to get into these exceptions a bit more when we look at the geometry behind it. All right, and the last thing for today is our formal charge. So the difference between the number of valence electrons on a free element, so if you just had a nitrogen hanging out by itself, and the number of electrons assigned to nitrogen in a molecule, or say it was sulfur, or whatever your carbon, whatever your central atom is. That is your formal charge. The reason we have formal charge, it's used to determine the most favored structure. There are multiple ways we can draw a certain structure, and we want to use the structure that has the smallest formal charge as possible. Also, a molecule or ion is most stable when any negative formal charge resides on the most electronegative atom. So to calculate formal charge, we're going to take the number of valence electrons in our center atom, or not even our center atom, but just the number of valence electrons that atom normally would have. We're going to subtract out the number of bonds that are bonded to it and the number of lone pair electrons. So let's see, sulfur dioxide, this is SO2. This thing is going to have 18 electrons. And when we bond these things together, let's see, I can tell I'm going to have a double bond here. Right, so I've used 12, 14, 16, 17, 18. All right, and I'm going to need to take a pair. I need to take a pair and make a double bond. I also can draw a resonance for this thing. So let's do that. This is also a valid structure. All right. Okay. So I want to look at the formal charge for each of these. And actually I can tell you the formal charge for these two is going to be the same when you look at all the atoms. Let's just calculate. Let's start with sulfur. So sulfur has 1, 2, 3 bonds attached to it. It normally has 6 valence based on the column. So we want to do 6 valence minus the 3 bonds. And then it has 2 lone pair electrons on it. These 2 electrons here. All right. So minus 2. Sulfur is going to have a +1 as its formal charge in this case. All right. If we look at the oxygen on the left in this first one here, so if we look at this oxygen also normally has 6. It has 1 bond, and it has 6 electrons, lone pair electrons on it. All right, so that is 6 minus 7. This gives us a -1. This is going to have a -1 charge on this oxygen. And then the one on the right, this one, has 6 valence minus 2 bonds plus 4 electrons. This one actually has a formal charge of 0. So the good thing is, the formal charge, +1 and -1 and 0, all adds up to give us a overall charge of 0, which is good because SO2 does not have a charge. That is one thing I don't think I mentioned before. Your formal charges should add up to the charge of your molecule. All right. Now the molecule on the right would have the same set of formal charges. It's just your 2 oxygens would be switched. Okay, let's try this with sulfate. So sulfate, SO4 2-, and I'm going to have 6 valence electrons for sulfur, 6 times 4 for oxygen, plus 2 for the negative charge. Oh man, what is that? It's going to give me 32 electrons. All right, so sulfur. All right. So this is going to be one where we're going to have to identify which structure is actually more stable. So I've used 8 of my 32. That means I've got 24 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4. Okay, did I do that right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4. Yep. And this has a 2- charge. All right, now, this is going to be a little interesting. If I look at my formal charge for sulfur, sulfur has 6 valence electrons, it has 4 bonds and no lone pairs. That sulfur is going to have a +2. And then each of these oxygens is the same. It's got 6. And then we've got 1 bond for each plus 6 electrons. Each of these oxygens is going to have a -1. So a -1, -1, -1, -1, and then a +2 in the center. Yikes. That's a lot of formal charge going on there. So the good news is this criteria is satisfied. A molecular ion is most stable when any negative formal charge resides on the most electronegative atom. That is true. All those things are on those. The issue is that atoms should have the smallest formal charge as possible. A +2 formal charge is pretty large in comparison. We don't really get much larger than +2. It happens, but not very frequently. We could actually draw something that's a little bit more stable than this. And it's going to be weird because we have to consider one of our exceptions to the octet rule. What can sulfur do when it's bonded to electronegative atoms? It can take on more electrons. It's a little electron deficient. Oxygen's electronegative. It's more electronegative than the sulfur. And the fact that we have 4 of them means all of our electrons are being pulled towards those oxygens, as we see from our -1 charge on each of them. We could actually draw a more stable version of our sulfate ion that would reduce our formal charges. If we try to draw it like this and calculate the formal charge, sulfur now has 6 bonds to it, which sounds crazy because it breaks the octet rule, but remember that's okay because of that d orbital for sulfur only, sulfur and phosphorus. Now the formal charge on our center atom is 0. We've decreased our formal charge. If I look at the left and right oxygens, I see that each of those have 1 bond and 6 valence, or sorry, 6 lone pairs, which means I've got a -1 and a -1. But then if I look at the top and bottom sulfurs, I've got 6 minus 2 bonds and 4 lone pairs. Each of those are going to have charges of 0. There is a way to decrease our formal charge and still have a stable structure. So just consider that. You sometimes might have a more stable structure because of the formal charge. This would actually be the better structure of sulfate because of its ability to complete that, start filling in that d orbital, and because it would reduce the formal charge. If you draw this one on the left, that is more than valid, but it's not the best structure. So just keep that in mind. All right, that is all for today.